should be on. So let me start by talking about the projects again. So a few people contacted me regarding project topics, but a bunch of people have not. So I think maybe around half the students have not contacted me at all about potential project topics. So it's getting quite late. So I think you definitely are supposed to be thinking about it, and I will try to send out some kind of individual messages to all the remaining people. Now, if you have contacted me about it, I think by now I replied to everybody. If I did not reply to you, if I missed your email or note on Piazza, contact me again, because I think at this point I should have reached everybody that I can find. I kind of had a bit of an overwhelming week in terms of amount of emails and things to respond to. So it's possible I missed your email. I don't think I missed anybody, but if I did miss you, I'm sorry, and email me again. Right. So if I did respond to you, then we should continue to until we to correspond until we settle on a final project topic for you. It's some people are settled and some are not. So that's okay, as long as we're in the process of doing that. For everybody else who did not initiate this, so again, I'll be probably contacting you individually. You really should be thinking about potential project topics, either from material we've seen so far, or any material we'll cover in the rest of the class, as mentioned on the syllabus. So you can look ahead and see if there's anything you're interested in there. So in general, again, for the project topics, I'm hoping for that to be some kind of open problem that you're working on, that you would work on and try to solve. But in practice, the final report might mostly consist of literature review about that problem. I just prefer to not have the original goal be merely a literature review, but make the original goal a little bit more, even if you won't necessarily be expected to achieve it. It's always good to start working on something new, start working on a problem. So that would be kind of the aim. And you are also welcome to work in groups, especially of two. And you can use Piazza as a coordination mechanism, or just tell me, I'm interested in this topic, I'm happy to work with somebody else, and I can try to match people as well. So that's also fine. Right. So just to make sure that the projects are in everybody's mind, especially if you haven't already been in contact with me about that. Right. So the second agenda item is to talk about kind of any feedback for me on the previous week's content. So this time I didn't post any written notes. And then I realized when making the video that the fact that I haven't made the notes actually made me a bit worse at making the video, because kind of a bunch of the material was not as fresh in my mind as it is when I had just, on a normal week, I just wrote the notes. Everything is totally fresh. So it's possible the video is slightly worse quality than normal. So I apologize for that. But if there's any feedback either on Miklos Santa's survey, if there's anything you kind of didn't understand, or if you found it too long, for example, anything like that, or on the video that I posted, then I'd be happy to hear it.
So broader picture question. Maybe I just missed this, but I didn't see the connection between these quantum walks and like lower bound techniques. It seemed more like an algorithms overview paper.
That's right. Yeah, it is an algorithms overview. Yeah. So quantum walks in general are they're an algorithmic technique, not a lower bounds technique. So
Okay.
I guess maybe I should have clarified that. So basically, it's not directly comparable to, say, polynomial method or adversary bound. It's the opposite, right? So those two techniques are techniques for lower bounding, showing the non-existence of a quantum algorithm, of a quantum query algorithm especially. And quantum walks are the opposite. They're a way to show that there is a quantum query algorithm. Yeah, so they're kind of the other side of the coin. Is like how would you design a quantum algorithm? So yeah, and so kind of one nice thing in general is that many times for both lower bounds and upper bounds, you don't need to think about really the quantum algorithm as a quantum object so much. It's possible often to design a quantum algorithm, for example, just by discussing a quantum walk on the Johnson graph and kind of analyzing these spectral gap and various other parameters like cost of updating and so on. So it's possible to design a quantum algorithm without really doing anything quantum yourself, just because other people did quantum stuff for you in the past. And similarly, it's possible to design a quantum lower bound just by, for example, using the graph formulation of the positive weighted adversary method, without touching any quantum amplitudes yourself, just using the fact that somebody else already kind of proved something for you about quantum lower bounds. And that's the common way to design both algorithms and lower bound, is to go through that. Actually, the most common way to design a quantum algorithm is to just say, okay, we just use Grover search plus classical stuff. So actually, the most common way is to only reduce it to basically classical algorithms plus Grover search. And so of course, there you don't need to know anything about quantum algorithms to do that. Yeah, but another way to design a quantum algorithm would be to design a quantum walk algorithm. And that is often also done without kind of remembering how quantum walks even work, basically only by walking on the Johnson graph.
It just seems
yeah,
like very different in flavor and sentiment, right? Where this is more like proving the existence of an upper bound, whereas most of the rest of the course has been like what is impossible sort of things.
Yeah, kind of. So I should have emphasized that more. So this is it was supposed to be kind of a contrast because we're doing too many lower bounds. So I thought we should do some algorithms. So I should have I guess mentioned that more explicitly. Yeah, thanks. So that's a good piece of feedback there. Yeah, but this is supposed to be kind of a contrast in that it's we're actually doing quantum algorithms and not only lower bounds.
Then okay, yeah.
Yeah.
I guess I'm a little maybe this is just me. I'm a little confused about what differentiates this course from the quantum algorithms course then. I feel like maybe it needs to be segregated stronger, right?
Okay. Yeah. I mean, who taught you quantum algorithms?
David Gossett. So he did
Okay.
a fair bit of lower bound stuff and walks and such, a little bit of Hamiltonian simulation. So I'm
I
just trying
see.
to figure out how to at least in my mind, try to get more out of this, right?
I see.
Than
I see. I see.
just
Okay.
yeah.
Okay. That's also interesting. I didn't even realize that he did quantum walks. So maybe that is a bit awkward. Okay.
Sorry.
Uh,
So I think for everyone else, basically, this is new, except for
okay. I see.
me, rambling
No,
at the end.
that's also a good piece of feedback. So I actually didn't. So I knew he did a little bit of polynomial and adversary bounds, but So I guess if we are also doing walks, then we do have a bunch of overlap. But I don't think we'll have much overlap for the rest of the course. Although since I don't know what he covers, maybe I'm wrong about that too. So,
Okay.
so for example, this week I was hoping to kind of do just a week on the largest possible gaps between quantum and randomized query complexities and sort of how far you can push kind of the biggest separations for quantum algorithms. There's some recent papers that kind of pushed this frontier, and I thought we would cover them. I kind of doubt that
No,
this will
that was not
cover it.
covered.
All
Yeah.
right. So, for example, this should be different. And then after that, we might just be doing communication complexity for the rest of the course. I don't know how much communication complexity.
I don't remember there being much, if any.
Okay.
I think that time was instead for Hamiltonian simulation stuff.
Right. So we won't be doing Hamiltonian simulations, for example. Yeah. And then you will see. So one other topic that possible we'll want to get to, but maybe not, just for time constraints, is basically either learning graphs or it's also kind of algorithmic technique. So it's how to design a quantum algorithm, but either via learning graphs or kind of closely related the upper bound version of the negative weight adversary method.
Okay.
Yeah. I don't know if presumably David Gossett would not cover it.
I don't think he did, but I assume it's similar to an STP sort of dual.
Yeah. It's
okay.
So the thing is, the reason why I feel like you wouldn't cover it is it's pretty query complexity specific. So if you're designing kind of quantum algorithms in real life, you might think of quantum walks as a reasonable technique. And of course, you might think of Grover search or Shor's algorithm as reasonable things to do. But it's unlikely that you will, think of learning graphs as kind of a reasonable thing to do, in my opinion. Just, you don't usually get good bound on the actual runtime, only on the number of queries. So it's fairly query specific. I think it's a decent tool to know, but I kind of wanted to prioritize. So there's so many things to cover. So I don't know if we'll get to it. Right. I did want to do some communication complexity as well. So we'll see. But okay. But it sounds like he at least didn't cover any of the rest of the topics. So
not that I remember. No, but
right.
maybe I'll find out.
So maybe the overlap with that course is only like 50% or something, or I don't know how much. Yeah. But I guess that's more than I thought. Okay. Maybe next time I offer this, I can try to differentiate it somehow more. Yeah.
I mean, the list of the topics isn't like put anywhere, from my understanding, either from quantum algorithms. So there's minimal way for you to have known, right?
I guess, but I guess there's only so many topics to go around in quantum computing. So we'd have to be fighting over some of these concepts. It's just like, no, I want to teach it. No, I want to. So
Yeah.
There's only so many. At the end of the day, it's not such a giant field. So yeah. Okay, but anyway, thanks. So that's also something for me to remember, that some people would have seen quantum walks already in a different course. Okay. Right. Okay, anybody else? Any feedback? All right, so if not, then let's jump right ahead to the presentations, so that maybe I don't keep you guys for too long. I know kind of I've expanded the time slot to an hour and a half, but it would be nice to let you guys go earlier than 6 if possible. So let's see. So who's giving the first talk? So right. So does anybody want to go first?
I'm fine with whichever position. It's
right. I don't know if there was much of an order in these. Was there? Does any of these three refer to the others? I feel like maybe they don't. Or is that? Or am I misremembering? Sorry, let me just. It's been a while since I posted these. Yeah, I kind of suspect that. Yeah, but there's no particular reason to go in one order or another. So okay, well, Lane, you just said that you don't have much of a reference, so I'll put you first in order to not kind of go with somebody who doesn't want to go first. So
sure. 1 second.
Yeah. All right.
How do I share? Let's see. Share content.
Which paper are you presenting again?
HK16.
All right.
You can see?
I can see, yeah, so hopefully everybody else can see as well.
Okay. So I'll be talking about efficient quantum walk on the grid with multiple marked elements. So the overall idea here is that we're going to have a bunch of elements which are connected in some topologically consistent matter. In particular, we'll consider either a torus or a two-dimensional grid. I'll get into what those exactly look like in a short bit, but some things to note are that our goal is to find some marked item. And if there's 5 of them, doesn't matter which one we return, we just want at least one of them. Or sorry, we just want one of them back with very high probability. Now, earlier attempts used the regular hitting time from Markov chains, but that mostly keeps its quadratic advantage when you have a single marked item in your set of vertices. And when you have more than one marked item, then you use this thing called the extended hitting time. And I'll get into one of the formulas that is typically used for it in a short bit. And oftentimes the extended hitting time and the regular hitting time are not terribly different. But if you consider something like the torus, the ratio between the two is about proportional to the size of the grid, which means that the quadratic advantage that you had from using a quantum algorithm in the first place basically disappears. So his paper's goal is to be able to preserve this quadratic advantage while still using, while still permitting multiple marked items. So, what is the problem in the first place? Well, the typical definition of the extended hitting time is 1 over delta epsilon. Epsilon is the error that you allow in not actually returning a marked item when you should be finding one, and delta is the difference between the largest eigenvalue and the second to largest eigenvalue in the Markov chain representing your graph. So in this paper, they report that you can actually make this a much tighter expression, or especially for things like the torus, a much tighter expression, as 1 over epsilon m, where this is a probability in being with your initial what's that called, stationary state, having each particular location be in a marked state, and that's the m in the subscript of the epsilon, times the escape time, which is a function of the original Markov chain p, as well as the marked states m sub pi. And m sub pi is the projection onto the marked states in the total stationary distribution. So the escape time is given by the following formula right here, which basically says what is the overlap of the stationary distribution's marked items with the eigenvectors corresponding to each of the eigenvalues. And so, if you have, this is a tighter expression for things like the torus. And another advantage of it is that this expression here uses the original Markov chain, but oftentimes in things like this delta parameter, you find it using the absorbing graph of the Markov chain, which says that you take the regular Markov chain for the lattice and you turn all the edges in the absorbing graph from being bidirectional nearby marked states to being only directed toward the marked states itself. So whenever any population arrives at a marked location, it never leaves it. So this has a couple of advantages because you don't need to compute that absorbing graph or the spectrum of it. You can just focus on the original Markov chain. So now, what are we going to consider here in terms of topologies? Well, we're going to consider a grid, which has each of these vertices having 4 neighbors on the interior. And so the weight of each edge coming out of it is 1/4. So it basically splits its population equally across each of its neighbors. But when we get to, say, the edge here, this vertex here shares with the one above down to the right, and it shares 1/4 back to itself. And likewise for the top one, and then in the corner, it shares 1/4 here, 1/4 here, and then 2 1/4s back to itself. So On the other hand, if the grid is pretty large, this is basically the same as a torus. So a torus can be thought of as a grid where the right-hand side has the rule that when you go one to the right, you just arrive back at the left-hand side. And when you go all the way past the top and go one further, you're at the bottom side. So topologically, it's equivalent to this shape, which is a donut in modern life, or a coffee mug, if you want to think of it that way. So in this case, all the vertices here have exactly 4 neighbors. There's no edge effects or anything. And so logically, when it gets really big, the two should have very similar runtimes for algorithms because the surface area doesn't grow that rapidly compared to the, I guess that's the perimeter does not grow that rapidly compared to the area. And then there's a third topology that we consider, the torus-shaped points. This is just a joke. Okay, so what is the central idea here? Well, what they do is they take the torus, let's say, it could be the grid instead. There's minimal difference because of boundary effects being minor. And they cut it up using, they cut it up into separate grids where these are basically utilizing the localized behavior of moving a random walk from some particular vertex. So each of these grids has a width roughly proportional to square root of t for some parameter t, which will be the length of time that we allow a point to randomly walk. So the idea is we basically break up the entire grid to a bunch of tinier grids. We initialize a point on it. We allow it to randomly walk, and a random walk for a time t has radius usually around square root of t. And so with high likelihood, we'll end up with one of the marked items being within the radius of the walking, radius that can be walked by our initial point. So then we just repeat this a handful of times, and we end up with still square root of the classical time with some log factors for the runtime now, which means we get the best of both worlds. We have a lot of marked states. We get the quadratic speed up, but instead of using the standard random walk techniques, we've broken up our entire grid into smaller pieces that we randomly search. Okay, and that's basically a summary of the paper. Questions?
All right. Yeah, so let me just say a few things about this. So first of all, I don't know how intuitive the setting is. So I mean, if it's kind of a natural setting for quantum walks, but for the context of this course, it may seem slightly strange to to just say, oh, we walk on a grid. So in terms of a query complexity model, you can imagine a kind of a situation where a graph is kind of provided to you in adjacency list format. So basically so let's say you have we have positions for all the nodes, and for each node, at the index of each node, you actually have, let's say, 4 things to query there. And the 4 things to query basically give you the address of the 4 neighboring nodes. So each node is basically going to have an address. But let's say that most addresses don't refer to anything. So if you just go to, so let's say the actual input is kind of be very long, and most positions you'll go to will just have like a star there that basically says, oh, this is not a real node. It will just say, oh, there was no real node here. This is a bad address. So like imagine the query complexity input is like this long string, and most positions in the long string will just say nothing here. This is not a real node. But let's say the very first one is going to guarantee to be a real node, for example. That's going to be where we start the walk. For example, like the center of the grid is just going to be guaranteed to be the very first node in the string. That's a promise. Now, each node actually comes with 4 pointers. So if you try to query the node, there's actually 4 things to query there, and there are 4 pointers. You can think of those as strings of length log n if you want, for roughly log n for, and then they address other valid nodes. So that's a promise. So I'm going to promise that if you have a valid address there, then it's going to address a valid node, and that node will also have the addresses of 4 neighbors. And we'll just promise that everything checks out, that you actually. So for example, if node A says that one of its neighbors is node B, the node B will also say that one of its neighbors is node A. We'll put that as a promise. So we'll just promise that everything's going to check out. But note that because I'm saying that most addresses link to nowhere, you can't find nodes by guessing their address randomly. If you try to guess addresses randomly, you'll just always see nothing here. Kind of, you'll always see positions of the string where it says nothing here. There's very few positions of the string where there's actually nodes there. So in that setting, the only thing you can basically do is walk from one node to one of its neighbors, basically follow from a node to its neighbor, and then from one of those neighbors to another neighbor, and so on. So you can, start searching from a node and see how far you can get. And now here, so suppose the kind of non-null nodes, the valid nodes of the string. Suppose we know there's going to be a grid of n by n of them, so they're connected to each other in a grid-like fashion, and that some of them are marked. So suppose, again, that's another thing you can query, whether a node is marked or not. So let's add that as another thing you can query for each node, for whether it is marked. And we're just looking for the position of a marked node, so that that's what you want to output. We can have that be a relational problem, for example, to output the address of a marked node. And any address of any marked node is a valid output. So that would be a relational problem, for example. So that's just how to set it up formally as a query complexity problem. Just to kind of make it more relevant to the rest of this particular class. So you could set it up in this way as kind of a formal query problem, and then you can ask, what is the query complexity of this task? How many queries do you need? And then you kind of realize that, well, one way to try to find this marked node is, well, if there were a lot of marked nodes, you can sort of just try a classical algorithm which searches at random until it hits one. So just go to a random neighbor and query it, and that would be even a classical query algorithm, a randomized one. Can find a random node using such an algorithm if there's a lot of marked nodes. So but we want to beat this algorithm, and we want to beat it by a quantum walk. And there's previously been known how to do this for either if there's exactly one marked item, then you would want the Grover speedup. You want basically to find it in only, let's say, order n queries up to log factors instead of n squared, which it would take to completely search this graph. So you want to basically get a Grover-like speedup. So for one marked item, this was known before this work. Or for any number of marked items, it was known on a 3D grid. So like in three-dimensional, if the graph was actually a 3D grid, then it was known how to get a Grover-like speedup for any number of marked items. So this paper basically also settles the problem for the 2D grid. And you have to analyze the quantum walk a lot more carefully than for example, in the survey by Miklos Santa. So here you'd have to analyze the quantum walk more carefully. So I should mention that the query complexity of this task is actually open up to this last log n. So I mean, okay, we know it's even for finding one marked item. So we know you can find it in root n times root log n, or sorry, root of the number of, so I guess it's n times log n, where n is if it's an n by n grid, then you can find it, the one marked node in n log n queries, or n log n steps of the walk, I guess. And the lower bound, there's of course a lower bound of n, just from kind of either Grover search or the fact that you have to walk n steps to even get to the edge of the grid. Like if the marked node is n away from the origin, then you just have to make n steps because you can never guess the position of a valid node. So that's okay. So there's actually two different ways to think of the lower bound, but the algorithm loses on the 2D grid loses a log n, and it's not known whether you need to lose the log n or not. So that's actually open. On a 3D grid, you do not need to lose a log n. So you can just there's a way to just a quantum walk will find you the marked item without losing any such log n. And on a 1D grid, actually, you're not going to get any speed up. So on the 1D grid, if the grid is, has n points in total, then to get to the edge of a grid, you actually need to walk n. There's no way to do it in root n, I mean. So there's no way to get a quadratic speed up over the classical algorithm that walks along this line. So on a 1D grid, you don't get any speed up. So then the question is, so here on a 2D grid, it was already known how to handle the case of one marked item, and here this was handling how to get also a speed up when you have multiple items. So you want a kind of faster algorithm than the trivial one, which either runs the classical one or runs the quantum algorithm to find one marked item, I guess. Anyway, so that's this paper. Any other questions for Lane or about this particular paper? Any comments? Okay. All right, Lane, did you have anything else to say about my description of it, or?
No, I mean, those were some of those were new things. Like it didn't really talk about the 3D case, I think.
Oh, okay.
In it.
Yeah,
so
I mean, this
that's
was
good insights that I didn't know about. Yeah.
Okay, yeah, the 3D case I think was handled by Aronson and Ambinas in some oldish paper.
I could believe that. Yeah.
Yeah. Yeah, I don't remember the name of the paper off the top of my head. Okay. Yeah, but it is kind of interesting to note that you can formalize this setting in query complexity, and so you can turn it into exactly a quantum query problem that just says, okay, what is the query complexity of this particular promise problem? Where the promise is a little bit awkward because you have to start talking about things linking to other things, like pointers that link to other things and whatever. But okay, I mean, at least you can formalize it in this way. Okay. All right. So next, I don't particularly mind who wants to go next between who's presenting now, either Zach or Abhishek. Is that true?
Yep.
Yeah.
No, I don't mind to go next. Yeah. Sorry.
Oh, okay. That was Zach, I think.
Yep.
Did you want to go?
Yep.
Yeah.
Happy to.
Yeah.
Also, I did notice some typos in this when I reread it right beforehand, but it's nothing major. But the paper that I'm sort of reviewing is covers nested quantum walks, and they introduce a quantum data structure to, I guess, improve some further or reduce the complexity, I guess, of the algorithm further from what it normally is. But the general question that is being asked is for a given set omega with elements in. You want to find all the marked elements that in this case would reside in the set M of marked elements, which is a subset of omega. I'll kind of go through this briefly because I think I might have prepared a little bit too much. But just a brief overview in the introduction of the paper, they point out that in general, quantum walk algorithms showed promise and strength and as a technique. And as time went on, different references here in the authors designed different algorithms to either apply to sort of specific use cases and or in this references case actually generalize the technique so it could be more appropriately or easily applied for different I guess, quantum protocols that people wanted to try to introduce. And in general, what is a quantum walk routine? For myself, I've not come across quantum algorithm design or theory before, so I thought it'd be good to just go through at a high level what it is. In this case, for the paper itself, in general, they define commonly a data structure, which is more or less an encoding from the input data you put into the algorithm to an answer to a graph theory problem. In this case, the paper focuses largely on the triangle finding problem. So for a given graph, you want to go through and find all of the triangles that might exist between vertexes in the graph. So the general algorithm setup is, if we're having an element U, I think this should be omega. If we take an element U that comes from the set omega, the goal is to determine if U in fact exists as a marked element in the set M. This method, as a quantum walk, as kind of previously said in the past talk, does walk around the graph, and in this case, the walk is performed by defining a Markov chain, and the probability distribution for it is denoted by pi over the graph. So we start out by defining an initial state, and it's just a superposition of all of the input elements U and the square root of the probability for that given U element being a marked, or in fact a marked element. And then from that, they will compute the data structure, which they just define mathematically as such, but not too important for later, I guess, discussions. Next, they iterate over, or they iterate 1 over the square root of epsilon, where epsilon is the probability for a given element to actually be in the marked set. And in each iteration, they go through and conditionally phase flip, or phase flip if U is in fact an element of N, or N. And then also within each iteration, they will uncompute the data structure, apply reflection through the entire state vector pi, and then recompute D. In this paper, I'll later talk about too that they have, actually, never mind, I want to misspeak. And I didn't know the scope of everyone's background in the class, so I did do a very, I think, brief and which seems now unneeded sort of review of just Markov chains and sort of graph theory at a very, very rudimentary level. But in general, Markov chains, you have different elements, and then you have probabilities of transitions between those elements that only depend on the present state of all of your elements and not the prior past. And then for graph theory itself, for some just general graph, call it G. The notation typically defines it as V is the set of all of your vertexes, and E is the set of all the edges you have within the graph. So the application that this paper sort of looks at is largely towards the triangle finding problem in graph theory, where there's been tremendous algorithm designs and efforts already done, and their goal was to show that this nested quantum walk and quantum data structure routine that they came up with is equivalent to all of these, or at least the ones that they compared these previous frameworks, and just trying to show a change in perspective on how to sort of approach some of these algorithm designs. So that said, they take a given graph that's already prior known, and they define a Markov chain construction over it to define the random walk that will be taken. And they walk over the vertices, and then they want to check to see if any of those vertices are connected to what they define as triangle edges, or in this case, they also use the terminology marked edges interchangeably. And then similarly, later on, as I'll talk about what their nesting method or term means, they can do this with vertexes, but it seems from what I understand about the paper that they can also do this with edges connected to a vertex. So they can walk over either different vertices or over different edges of a given vertice to see if there are any triangle connections or edges that are existing. And they also consider, I won't go into this explicitly, but they do consider checks where if you find 2 out of 3 edges and you don't know, without knowing the third edge, you don't know if it's in fact forming a triangle with the vertices, that you can go ahead and account for it, and then introduce certain routines to go back and remove false flags, but they didn't explicitly go into any sort of approach on this. And then finally, if a vertice shares 3 edges, or if 3 vertices share 3 edges, obviously it forms a triangle in this case. And in this paper too, which I already briefly mentioned, but just to reiterate, the data structure that they're talking about and later going to define as a quantum, define as a quantum data structure, encodes the solution to all of the triangle vertices. And there's a couple of different methods that they looked at. Specifically, they looked at one paper that approached an algorithm designed for solving the triangle finding problem, and then another that used a learning graph approach to do that. And just kind of to surmise the work's contribution, there are 2 main, well, I guess 3, but the 2 main goals explicitly said in the paper was to introduce the concept of a quantum data structure, which up till now had not been explored, at least in published work, and then to apply a quantum-based walk where it essentially consists of 2 looping routines, an outer and inner looping routine. They call these walks, and the outer walk either initializes or updates the set of vertices or vertex edges that they want to check. So the vertices that they're actually going to go and check the edges for. And then the subroutine or the inner walk checks all of the edges for each vertex to see if it is in fact marked. And just to briefly go into the quantum walk framework in the case of this specific reference, which is closely related to what the paper mainly puts forth with their own work. If we're given a reversible Markov chain P, again, with it having a stationary distribution pi, as kind of previously mentioned, we'll also define a data structure for X input. It's worth noting that this data structure is just a mapping between the set omega to some Hilbert space where they define as HD. And finally, the overall data structure itself is defined as the total set of all transformed elements from the input. The 3 main, I guess, aspects of the algorithm that they focus on when they start talking about the complexity of it is, and they use the terms complexity and cost interchangeably in the paper. They talk about the setup cost, the update cost, and the cost of checking to see if you have a marked element. And for the algorithm itself, again, like previously said, for a general quantum walk, you can construct an initial state where you have some element from your input in a left register, and then you have some starting element, in this case 0 in your right register, and then you have your data structure itself. And then then they define, so once you have this state set up, now you want to make updates to it and ultimately search over all the elements in the input. And to do so, they have two unitary operations that they define. One updates the actual vertex itself. So in this case, we go from some starting vertex to some new vertex in a general way. And then there's also a unitary operation that will also update the data structure itself. And then the final main step to the algorithm of a general quantum walk is to go through and check to actually see if any of these elements are in fact part of the marked set. And if that is the case, again, the phase is flipped. And the main difference between sort of a general quantum walk and what was initially put forth in this paper is they do allow for this data structure to in fact be quantums, and they'll later define as a linear superposition of other data structures. And they also, in this case, have a unitary operation for each register, compared to the paper that this was based off of only had a single unitary operation for both registers. So just a general framework for the nested quantum walks. I kind of previously mentioned that the name is pretty self-explanatory, where it's one quantum walk nested in the other. So in this case, they have this relationship defined outright, where if we have, this is m to the power u and subscript x, but if we have a non-empty set where this is the, well, I'll define it a little bit later in a second, but if we have this non-empty set and we have an element in our set omega, then we in fact know that, u is a marked element. In this case, they use the terminology for mux as a witness for u being an element of the set M. I've also seen this term used as, and I don't know this to be correct, so correct me if I'm wrong, but you can use certificates to check to see whether or not an algorithm gives you back essentially like a completed yes, no, incomplete indicator on some algorithm you've designed. But anyways, the reason I set this up is it just sets up the concept that they have a inner subroutine or a nested subroutine that they're running, and it gives you information about whether or not the element is in fact marked. So with the yeah, sorry,
Zach,
I don't mean to run on.
Yeah, no, you're just kind of going over time.
Okay,
I wonder
sorry.
if you had some kind of concluding statement you want to go to. Yeah, sorry, I just basically kind of have to cut you off because of the time constraints.
No, I completely understand.
Yeah.
Concluding statement, I'll just say by implementing this nested algorithm and having a data structure for the outer walk that is defined as a linear superposition of data structures for the inner walk, they're able to essentially take out the cost of setting up the inner nested walk, and they don't have to run that routine over and over. So the initial state of the inner walk is always the same, and they're able to actually pull that out and not multiply it by this factor of 1 over root epsilon 1, where that's for the outer Markov chain. And so that was the main takeaways. By doing this nested approach, they're able to transfer the load for very expensive routines to only run a few times, and then other routines that are cheaper to run, they can throw them in the inner walk and speed up their algorithm in that way.
All right, thanks. So any questions for Zach? Okay, so yeah, I mean, I think the main idea is hopefully clear from Zach's presentation. But yeah, the idea is, so as Miklos mentioned in his notes, and I mentioned in the video as well, then in quantum walks, you generally have, I mean, you can sort of specify the total cost of the walk in terms of these, the cost of the pieces, like the update cost and checking cost and setup cost, as well as the number of marked items you're looking for, and this spectral graph for your graph. And I guess the main thing that's going on in this paper is that they're basically saying, okay, so suppose first, say your checking cost, you want to check if an element is marked. Well, you can design your quantum walk such that this checking step is implemented by another quantum walk. So then you basically have nested quantum walks. You have kind of a bigger quantum walk on the outside, and then whenever that outer quantum walk wants to check something, then it runs as a subroutine an inner quantum walk. And you have to be a bit careful that, because the outer quantum walk actually is going to do everything in superposition, and you have to make sure that it still makes sense to kind of run algorithms as subroutines within a superposition over which algorithm you're even running. And so this is a setting that happens a bunch in quantum algorithms, where you're trying to, in different scenarios, you often want to compose quantum algorithms. You have an outer quantum algorithm, and it wants to call an inner quantum algorithm as a subroutine, but it's going to do that in superposition on say different inputs each time, and you don't want the cost to kind of blow up. You want the cost to just be the product of the costs, for example, of the outer algorithm and the inner algorithm. Even though the inner one is being run in superposition, this needs to kind of not break anything. And in general, this is true for quantum algorithms. So you need to be a little bit careful with the analysis. And Zach went over a little bit of the details of that, of how they had like two different registers on which they're acting there. But you have to be a little bit careful with your analysis, and it just generally will. The intuition is it will turn out to hold that you are allowed to run an outer quantum algorithm, even if it needs to kind of call an inner quantum algorithm in superposition. So generally this is not a problem, and so this is a kind of quantum walk version of that, I would say. Yeah, I don't know. Thanks for the presentation. Anyone have any more questions or comments on this paper? I'm not sure what else I have to say. Okay, so that's okay if not. Before we do the last presentation, while I still have everyone here, yeah, I forgot to ask for volunteers for anybody wanting to present next week, in next week's meeting. So the topic for this week will just be kind of we'll have 3 papers to present. They will be about kind of the largest gaps you can get between quantum and randomized algorithms, or we will have the separation between BQP and pH will probably be one of the papers as well. So just kind of this is the largest separation between quantum model and kind of the strongest possible classical model that we can still beat with the quantum algorithm, so far as we know. Are there any volunteers to take up any of those 3 papers? I guess I didn't list all the papers yet, but I'll put them up shortly. Does anyone already know that they want to present next week? No. Yeah, I usually ask this at the beginning. I'm not sure if everybody is still. Some people are kind of away from screen or something, but okay. Well, it's. I guess a bunch of people who are present have already presented once. So I will pick myself and prioritize the people who haven't presented yet. So there's still maybe 2 or 3 people in the class who have not yet presented once. So we'll prioritize them, and just of course as a reminder, everybody, the goal is that you will present exactly twice this class. So if you presented once, expect to present once more at some point. You know, if you haven't presented, you're probably presenting next week. I will look through the list and pick people. If you've presented twice, then you definitely won't be presenting next week or again at all, except for the final project presentation. So we'll have those around the last week of class. Okay, so let's go with Abhishek's presentation, unless anybody has any comments on anything.
So I had one question.
Okay.
Regarding this paper. So this paper is shows that the bounds that were reached by the learning graph approach were the same as the bounds sort of reached by this nested quantum data structure approach. Has there been any work in like trying to prove that both of them maybe are equivalent or something like that, or are there cases where separations between these two approaches are known?
For this paper Zach presented, you mean, or?
Yeah.
I think so.
Right. Yeah, Zach, I don't know if you had any comments on that, or I can try to answer. Or
and I don't know if I understand the question correctly, but in the paper itself, or I mean, most of the comparisons they did, they were just trying to show that their method could show equivalency, at least for computational complexity, with, like in your questions case, the learning graph approach. So they just want to go through and show that, you know, this is a new perspective for trying to approach these algorithm questions or problems, but then it is equivalent to all the previous work done, if that answers your question. They didn't talk about sort of, I think, a bounding case explicitly for the learning graph problem, but they did talk about bounding case for the inner subroutine could be ran at most polynomial in, and that allowed them to also make sure that some of the other algorithm approaches they compared to, they could actually get equivalent complexity orders.
Yeah, so I mean, I guess Abhishek, if you're asking more generally, if it's plausible that every learning graph can be converted to a quantum walk and vice versa, you know, then well, it wasn't really studied in this paper, but I think, you know, part of the problem is that learning graphs, in a sense, the framework is not powerful enough to use all the information you have about a quantum query problem. It, in a sense, only uses kind of the certificate structure of a query function. So it's kind of a slightly limited framework in that it only like uses certain informations about your function, and therefore can't possibly give you the best upper bound in all cases. So that sort of always allows quantum walks to beat learning graphs for some functions, I guess, just because the learning graphs don't know everything about your function for sort of fundamental definitional reasons. In the other direction, though, learning graphs are kind of, for the information they do use, then they're in principle, you know, tight out of techniques that only use that information. So basically, they only know some things about your Boolean function, but for Boolean, for any quantum algorithm that only knows that information about the Boolean function, you cannot beat learning graphs in some sense. So they're in a strange sense, they're kind of tight within their setting. And quantum walks, I don't believe, are known to be tight. Depending, well, it's not. Quantum walks are not really a concrete, well-defined framework, right? Because we just say, okay, you know, you're running this walk, and then you have to define a checking routine and an update routine and whatever. But since those can be arbitrary algorithms, then I guess in principle you can, you know, you can run any arbitrarily complicated quantum algorithm within the checking routine or something, and then, okay, so I mean, maybe in some trivial sense, you can put all the complexity of your algorithm within that checking routine or something, and therefore simulate any other quantum algorithm just by putting that other quantum algorithm within the checking routine or something. So, you know, in some sense, I'm not sure if there's any non-trivial way for quantum walks to simulate learning graphs. Yeah. So, but in this particular case, yeah, then the two approaches ended up being sort of equivalent. But with quantum walks giving you actual better bounds on running time and not just quantum query complexity, if that's ever something you care about. So like, what is your actual quantum circuit in the end and how many gates does it use? Then quantum walks gives you generally better bounds, and learning graphs generally gives you no bound at all, so like exponentially bad bounds. So if you only care about query complexity, then that doesn't matter. But if you ever are going to want to try to implement this algorithm for some reason, then the quantum walk framework is usually better. Okay, any other questions or comments on anything? All right, so if not, so Abhishek, did you want to present?
Yeah. Can you hear me?
Yeah.
Yeah, sorry, I clicked on the share button and my Teams crashed. But yeah, this should work now. Can you see my screen?
I cannot see your screen right now.
Is it visible? Oh, no.
I don't see it actually. I don't know why.
No, not yet.
Why is this? Let me check one last time. It's not visible.
Nope.
No. Don't know why.
Let me quickly turn off Teams and try again.
Yeah,
Okay.
sure.
Yep, we can see it.
Oh, great. Yeah, I logged in through my browser and that worked for some reason.
Okay.
Yeah, so I'll be talking about this paper by Ashley Montanaro about speeding up backtracking algorithms using quantum walks. So I guess first, what these algorithms are trying to do is solve constraint satisfaction problems, and a very naive approach towards solving a constraint satisfaction problem would just be looking at all the exponential possible assignments. So we could basically draw this tree and set x equal to 0, and we can basically look at all the ending nodes here and then verify which one of them actually satisfy the constraints. But in the worst case, no matter how we traverse this tree, this will take exponential time in the number of variables. So one way to actually get around this issue is one way to reduce the size of the tree, not not in terms of the scaling, but just in terms of in practice, reducing the size of tree is assuming that we have access to a few more predicates. So one of the things we have access to is something where we can put the assignment of our variables, and we can leave some of the variables unassigned. So that is what this star symbolizes, and then that would basically give us true if this is true no matter what the unassigned variables are set to, false if it's false no matter what the unassigned variables are set to, and indeterminate, which means that we don't know. We'll have to assign a few more variables to see whether this will turn out to be true or false. Similarly, we can assume that we have access to some kind of heuristic that once it takes input what the current assignment is, then the heuristic tells us what is the next variable we should try to assign. So if you look at this exhaustive tree, and if we had used what we had done was that at every node, when we assign a variable, we had actually checked whether p is true, false, or indeterminate. And if it was false, we just didn't go forward, or if it was true, we just didn't go forward. We can sort of see that the tree would have been reduced to this. So, and then because no matter what we set z to here, for this case, this will always be false. So there's no need to actually check the future, the other nodes. So this is basically a very general way of looking at backtracking algorithms for solving constraint satisfaction problems. And if you look classically, if let's say t is the number of nodes in this backtracking tree, so we define this thing to be the backtracking tree, and if t is the number of nodes, the number of times we had to query p and h, so like compute p and h, was t, which is the number of vertices here. So that's sort of what our classical bound looks like. So what this paper shows that like the main result is that there is a bounded error quantum algorithm that finds assignment if it exists using these many calls to PNH. So generally we think of t, which is the number of nodes in this backtracking tree, as an exponential in terms of n. So we are actually getting like the square root advantage because this is just a polynomial. The other part is just a polynomial or n. So in the worst case, this gives us a near quadratic speedup over the classical algorithm that we considered above. Previously, what was known about such techniques was there was exponential separation known, but for specific trees between a quantum backtracking and a classical backtracking algorithm, let's say, that uses these p and h functions. However, now we know that there's a near quadratic speedup for over any tree. And the main idea regarding how it works is that we use a quantum walk. So in our quantum walk, just to set it up, and what it looks like is that the graph is the backtracking graph, the backtracking tree. The marked nodes are all the nodes in which the predicate p evaluates to true. So those are the nodes we want to find. Those are the satisfying assignments. And the initial state is the root. So the root is basically where all the variables are unassigned, and slowly, as we go down a level, we assign variables based on our heuristic. However, we can't simply just use the approaches that we learned in lecture or in notes, because in those approaches, the graph was already known, which was mostly the graph was already known, which was the Johnson graph, and the problem basically specified which node was marked, the marked node. And another difference between this quantum walk and the quantum walk we saw in class is that the initial state in those was a sample from the stationary distribution, while here we are setting the initial state to be the root. So actually, like those search algorithms don't work in this setting. So so in this paper sort of proposes a new algorithm which works in this particular setting. And so first I'll just talk about a detection algorithm. And what the detection algorithm does is it detects whether there's a mark node or not. And then I'll be talking about how to convert that into, there's a very trivial way to convert that into an algorithm that actually finds a satisfying input. So we define RA and RB to be essentially the mixing and update operators. And they're different based on which level the node is at, whether it's an even level or an odd level counted from the root. And if there are any questions, we can talk about the specific structure of what RA and RB is, but we can just think about them as spreading. So if you're on a node, we basically spread probability through its children, more or less. And then the main result that we get here is that if we apply phase estimation, so this should be estimation, phase estimation to RBRA, so this product, this unitary, on the root node with this precision. So that's the main idea, that we want to apply phase estimation. And that would, in some sense, help us detect whether there's a mark node or not. The reason that works is because of two technical ingredients. The first technical ingredient is from Bilov's paper, which basically says that we can show through explicit construction of the eigenvectors of RB and RA that if there is a mark node in our backtracking tree with arbitrarily high probability, the eigenvalue of the root node will be 1. So essentially what that says is that the eigenvector which has eigenvalue 1 has a large inner product with the root node. However, and then we can also show the opposite, the other direction, that if there is no marked node, with arbitrarily low probability, the eigenvalue of R will not be 1. So essentially, by doing phase estimation and computing the eigenvalue of RBRA on the root node, we can use that as a proxy to determine whether there is a marked node or not. Then all that remains to show is that we can actually do phase estimation of RB and RA using P and H, because we are not given RB and RA, we are given P and H. But and then in the paper they show that RB and RA, because they're doing mixing over the children, they can be implemented efficiently by just knowing what the children and neighbors look like, and which nodes are even and which nodes are odd. And we can completely use P and H to determine the action of RB and RA. So by basically combining these two ingredients, we basically say that get that there is a bounded error quantum algorithm that finds that basically tells us whether there is a satisfying assignment or not, and it uses only O of square root Tn calls of P and H. The reason we get this square root is basically because this is the precision we require, and the reason we require that precision is because only then would we get this Belov statement. So once we have an algorithm that detects whether there is a satisfying assignment or not, we can easily convert it using binary search to an algorithm that finds us a marked node by basically starting at the root and then slowly traversing the tree. And we know that would take like an extra n log n factor, and that's where this n becomes an n3/2 and the log n comes. So overall, what this algorithm shows is the classical algorithm would take O of t time. O of t calls to P and H, while here we sort of reduce it to O of square root of t multiplied by some polynomial of n. And I guess one of the key features, at least for me, was this thing that I guess it didn't use just the Johnson graph. It actually had to do something different. And that was, I guess, the main feature for me, or what made this paper different. Yeah. Any questions?
All right. Thanks.
I can open up the paper.
Yeah, any questions or comments for anyone? Yeah, so I mean, I guess I feel like Abhishek's summary was pretty good. This paper, it kind of tries to improve a whole class of classical algorithms in a sense that, many times classical algorithms have this kind of backtracking nature, where they kind of search for something and kind of retreat up the tree when the search fails. So I think maybe it's related to branch and bound algorithms or things like that. For classical algorithms, they often have this form. So basically, various classical algorithms or classical heuristics tend to have this structure, and so this is sort of trying to give a black box improvement that quantumly that says, okay, whenever you have such a classical algorithm, you can improve its runtime by basically doing a quantum version of it. And now the improvement is only polynomial, so you only get it's only at most a Grover-like improvement. It actually seems to be a bit less, and that's kind of generally the case when you're trying to improve a general class of classical algorithm. But still, even getting a Grover-like improvement is often difficult. And so it's kind of neat that such a wide class of classical algorithms can be handled like this. And I think it's a kind of a good example of quantum walks being useful not on the Johnson graph. So and of course we've also had the quantum walk on the grid for the first presentation this week. So when I say in the video that you should be walking on the Johnson graph, that's only in the sense that that's the first thing you should be trying. It's not true, of course, that all quantum walks always want to work on the Johnson graph. But that's kind of the easiest way to design one, and often the first thing you should be trying. Yeah, I don't know what else to say about this paper, actually. Anybody else have any questions or comments for Abhishek? Okay, so well, thanks, Abhishek, for the presentation. And so if nothing else, then I guess we will stop here. Just a reminder, we do need... Oh, yeah?
I have a quick question. Will there be a homework posted soon, or is it going to be postponed / canceled?
Yeah, I didn't manage to make it, and I'm going to be very busy the next few days. So I will hope that I can make it for next week, but I'm not even sure about that. So I will. Yeah, I'm very bad at this. I'm going to try to post it soon. I am a bit more worried though about the projects. I was hoping everybody will have topics by now, but not everybody contacted me about it. So I will contact you if you haven't. So that's kind of my first priority, is to make sure I do that first, and to have kind of everybody set up to work on something. And I will try to post a homework. It won't be too much of a big deal. It won't be a giant long homework. It will probably just have a few questions on it, better viewed as kind of practice than as kind of a true difficult assessment. So don't expect too much out of it. It's possible you'll only have how much time do you have left in the class? I'll give you at least 2 weeks to work on the homework, but I was hoping to give you somewhat longer, but depending on time constraints, I do want it due before the last day of classes, just for administrative reasons. So we'll see. It might not be that you have much longer than that. No, it's not coming before next Monday. How's that? Just because I can't possibly finish it in time. Too many other things this week.
Okay, all good.
Yeah. Okay. Right. So yeah, that's also the only thing I was going to say was again a reminder on the project and I will post some content for the upcoming week and as well as the readings, and most of the maybe even all of the volunteers for presenting will be people who haven't presented yet. We'll see if we actually have 3 such people. If not, then if we only have 2 such people, then of course somebody who presented already will have to present again. So I'll contact you about that if you're presenting. All right, and you know, as usual, there's an anonymous feedback thread on Piazza that you guys should be using if you want to, you know, tell me that something is horribly wrong with my organization or the notes or anything. And also, you can use Piazza for finding a project mate to work with, somebody to work with on the project. Okay. All right, so let's stop here, and I'll see you all next Monday. All right. Bye.